Hello again, this is Math 2231 remote delivery for April 21st, 2021, and this is use substitution, part 3.
Let's start
and
with
again, I
three
encourage
problems
you
to
use
do
these both as you're listening to the
lecture,
lecture, pause,
and as you're trying to do the
go.
problems.
It will increase your understanding by trying them. So please give these a go. We'll see how you did. Let's see how you did. Well, when you look at this problem, this is the one we're trying to do, you see that 2t figures prominently in each one, and we know what these antiderivatives are. So the substitution that will work in both terms is u equal 2t. That means that du is going to be 2 dt, and solving for dt, that'll equal 1/2 du. So that 1/2 can be pulled through the entire integral. That's the 1/2. And then this is e to the u, secant u, tangent u, du. And the antiderivative of this is e to the u. The antiderivative of this is secant u. You see, you have to know these things cold. And then it is plus c. And for the problem to be correct, we have to return to our native variable, so we back substitute for u. And that's the final answer to that problem. Here's the problem we were confronted with. And notice that the sine t is multiplied all the way through, and in the first two terms we're going to need that for a u substitution, so we're motivated to let u be cosine of t. Now that means that du is equal to negative sine of t dt. Don't lose that negative sign. We're going to divide all the way through by minus sine of t, and we get du over minus sine of t is equal to dt. So let's make that substitution. The minus can be pulled all the way through. I have 4u cubed, and then it is times du. You see, magic happens because the sign cancels here and cancels there. Here we get, again, magic happening. This is going to be 6u squared. And here you see the sine t is contained within the du, and the minus sign comes from here. So we're good with that as well. So that is how the substitution happens. And again, we made magic happen. We integrate each of these, leave the minus sign out in front, add 1 to the exponent, and divide by the new exponent. The 4 cancels. Add 1 to the exponent, divide by the new exponent, and the 3 will cancel into the 6 and leave 2. And here you add 1 to the exponent, you get u to the 1 over 1, and that's what we have, plus c. And then for the problem to be finished, we have to go back and resubstitute our native variable, which was u equals cosine t. We substitute that all the way across. This is our final answer. Okay, here is the problem that we have, and we notice that the same substitution will work on both terms. If we let u equal x squared plus 1, then du is equal to 2x dx, and if I solve for dx is equal to du over 2x. So if I make that substitution the 1/2, the 2 in the denominator pulls all the way through. Magic happens because both of those x's cancel with this x in the denominator. The x's in the numerator cancel with the x in the denominator. And so this is what we get after we do the substitution. Again, magic happened. This is 1/2 cosine of u plus 1 over u du. Okay, so the antiderivative of the cosine is the sine of u. The antiderivative of 1 over u is the natural logarithm of the absolute value of u. And what I get then is when I back substitute, reversing my substitution into my native variables, which I must do to get credit, this is what I get for my final answer. These absolute values here are not really required because x squared plus 1 is always positive, but don't worry about that. They don't hurt anything. That's your final answer. 2 more problems for you to do. Again, hit pause, try to do these problems, and we'll return in, see how you did. Let's see how you did. Now, this first term is just x squared dx. We know how to do that, so we're going to just leave that alone. But here I need to do a u substitution. So here I'm going to let u equal 1 minus x, then du is going to be minus dx, and then dx is going to equal minus du. So now I'm doing a u substitution. Now the first one, we knew how to integrate this for a long time. Add 1 to the exponent, divide by the new exponent, so that is 1/3 x cubed. Here, I did need the u substitution though, so that is minus e to the u. And then this is plus c. And then I must return to my native variables to get credit for the problem, so I put what u was in terms of x. This is the final answer. Here we have a problem where what is happening is we do see, as we saw in an earlier example, that x squared plus 1 is prominent in both of these. But you see, it really is not going to work. Let's just try the first one, but let's try the substitution to see how it will go. If we let u equal x squared plus 1, then du is going to be 2x dx, and dx is going to be du over 2x. Now that's going to work nicely in the first integral as it did before, because we're going to get 1/2 times the, and it's cosine of u. Magic happened because this x cancels with that x, and then we have a nice integral for us to do. But in the second one, if we tried to do that, we would find that magic wouldn't happen because nothing will cancel with this x. So we have to do something different on this. But fortunately, we studied our integral formulas, and we know that this is a formula that we remembered, and this one is going to be the inverse tangent of x. So we do it term by term. This 1/2 is only times this one. This one is simply the inverse tangent of x. So next step, we get this as 1/2. The antiderivative of the cosine of u is the sine of u. This is the arc tangent of x, and then this is plus c, and returning to our native variables as we must to get credit on the problem, we receive this as the final answer. Okay, here are 3 more examples for you to do. Please hit pause and or return and see how you do. Please give these a go. Let's see how you did. Now, in this one, this is best done by breaking it into 2 terms, because the substitution is going to be different in each one. In the first one, this is the substitution that will bear fruit. U is equal to minus z. That means that du is equal to minus dz, and that means that dz is equal to minus du. But that's going to work in this first one. In the second one, when we're integrating this, the variable that we need to substitute for is z over 10. So we're letting v, we're going to use a different letter just not to be confused. So v is equal to z over 10. dv is going to be 1 over 10 dz, and that's going to tell us that dz is equal to 10 dv. Now, notice that we used different letters in each one of those. We talked about that. So let's keep going then. So the first integral, notice I have a minus sign here, so when I change variables, magic indeed does happen, and I get the minus sign I pull through, and I'm left with e to the u du, which I know how to integrate. And here I pull the 10 through the integral, and I'm left with secant squared of v dv. I know how to do that. So that is tangent of v. So the answer in terms of u's and v's is minus e to the u plus 10 tangent of v plus c. And returning to the native variables, note that there were 2 native variables though. This is going to be minus e to the minus z plus 10. This is going to be tangent, and that's going to be z over 10 plus c. That is the correct answer. Here's the problem that we're confronted with here, and notice that again there are 2 terms, and as it turns out on this one we're going to have to do 2 separate substitutions on each term. Let's look at the first term. Here the substitution you should have done was u is equal to 1 minus 2 cosine of w. That means that du is equal to 2 sine of w dw. And if I solve for dw, that is du over 2 sine of w. So when I do that substitution, this 2 gets factored through. Magic does happen because the sine of w cancels with, this sine of w cancels with that sine of w, so magic happens. I'm left with u to the 1/2 du. Now, the next integral, though, which is this one, You need a different substitution. It's going to be v equals 7w plus 2. That means that dB is equal to 7dw. That means that dw is equal to 1 over 7 dV. 1 over 7. Pull it through. dV. I'm integrating with respect to v, and again, magic happens. Okay, so here I add 1 to the exponent and divide by the new exponent. That's going to be 2 over 3 e to the 3 over 2, and that's also times this half to start with. Plus this is 1 over 7, that's the ln of the absolute value of v plus c. Returning to my native variables, I write the final answer this way as a simplified answer. Alright, here is this example. We're going to do this term by term, but you notice that there are two terms, so I divide this denominator into the numerator. So this is 10x over this plus 3 divided by this. So you see I have two integrals to do, and they're going to be different. On this one, I need magic to happen, and so what I'm going to do on the first one is I'm going to use the substitution u equal x squared plus 16. If u equal x squared plus 16, then du is going to be 2x dx, and du over 2x is going to be equal to dx. And magic will happen because this x in the denominator will cancel with that x in the numerator. The second one needs some work, and so let's talk about some of the work that we're going to do. If we factor 1 over 16 out of this, I've turned this into a form. Now I can't use the same thing because you see that same substitution isn't going to work because this x wouldn't cancel. So I have to do something else, but I realized, oh, I have something squared plus 16, so if I factor out the 16, I will have 3 is sitting up there for a while, but this is 1 over 16 that I factored out of the denominator, so this is x squared over 16 plus 1. So you see the substitution we're going to use there, we're working towards getting an inverse tangent, is v equal, v is equal to x over 4. That means dv is 1/4 dx. That means dx is 4 dv. So let's pick up the problem then again. So here, I changed things around, so I just have 5. You see this 2 in the denominator will cancel into the 10, make it 5. So it's 5, the integral of 1 over u du, and here whenever I do the simplification I get 3 over 4. I factored out all those numbers. And this is the integral of 1 over v squared plus 1 dv, so this is going to be 5 ln of u plus 3 over 4 times the arctan of v plus c. When I return to my native variables, I get this as my expression. That's the end of part 3. See you